Hi, my name is Arish Virani, and this is my fifth lab for physics, the rope swing. So for an introduction, the purpose of this lab is to model and validate the 2D motion of a jumper on a fixed length rope pendulum using tracker XY data, predict the motion and compute speed v and rope tension t for an ideal non-stretch rope, overlay the model with the measured trajectory, and compare x and y trends. Estimate rope stretch near the bottom via the spring approximation s approximately equal to t upon k, order of magnitude, decompose net force into tangential and radial components, and comment on the effect of light damping or air drag or air resistance. So a brief preview of our results. We overlay a simple pendulum model, fixed length rope, gravity, optional light damping on the tracker XY data. The simulation captures the overall arc and timing, predicts peak speed and largest tension near the bottom, and uses a spring add-on to estimate small rope stretch. Remaining offsets, phase, late time drift are consistent with calibration, perspective, real elasticity, air drag, and body posture. Effects not included in the model. These are some of the graphs that are as a result of our glow script code computation. So the physics principles and formulas that we use Newton's second law, treat the jumper as a point mass on our tracker software, attached to a massless rope of fixed length. We step time by using the tangential component of the net force to update angular motion. On the right, the first formula is Newton's second law in momentum form. The second defines momentum. Force decomposition. In our model, the rope is constrained, so only gravity acts. We resolve gravity into r hat and t hat to find unit vectors from the anchor, r hat along the rope and t hat perpendicular. Gravity provides g, t hat is for the tangential acceleration. The rope constrains the radius. So the angular update, compute alpha g times t hat upon L naught, then update omega and theta. Position velocities are calculated using formulas derived on the right. The tension ideal rope form radio, t is equal to m brackets v squared upon L naught plus g times r hat. We compute tension and we don't feed it into the motion. And the stretch estimate for the actual real rope after the run approximation, rope stretch with Hooke's law. This is for discussion only. Trajectory remains ideal. Okay, so here's the observed model that we get via our tracker software. Our system is the human jumper, and our surrounding is earth, gravity, rope plus anchor, which gives us the tension, and air, which is an optional drag that we may or may not use. So the models and procedure: jumper is a point mass on a massless, inextensible rope of fixed length, 45.72 meters or 150 feet, anchored at the tracker measured point. Forces included are gravity down and rope tension along the rope. Optional tangential damping exists, but is off for the main run. State we update was angular position and angular speed, and we convert to xy position and velocity each step. Outputs we model xy speed over time and tension over time. A stretch estimate using a chosen k is reported for discussion only and does not affect the motion. Tracker recalibrated scale and frame rate, mark the jumper each frame and exported t, x, y without the headers in a CSV or Excel file. And the glow script code computation, we load these files with the button set m, L naught anchor initialized from the data frame, shows dt from the median frame spacing, and simulated over the same time window. And for comparison and plots, we overlaid model versus data for x, y, and the plotted speed and tension, reported max stretch for real rope discussion, and adjusted anchor slightly for best overlay. Okay, so here's our glow script code, and the initial conditions are set as following. The mass of the jumper is 80 kilograms, g is equal to negative 9.8 in the downward direction, L naught is equal to 45.72 meters, which matches the 150 feet of the rope length. B tangent is set to 0, k is equal to 3000 for the stiffness, and the real rope for now is set to false. And I load the tracker TXY CSV, pick a start rope, place the ball on the circle L naught from the anchor, and estimate the initial velocity from nearby data points. For the ideal rope, I remove the radial part. The time step, delta t, comes from the data spacing. Each step, I rebuild geometry, r hat, t hat, compute forces, gravity plus optional tangential drag plus spring if the rope is stretched. We sum to f net, and then update acceleration, which is equal to f net upon mass, velocity and position using the velocity and position update formulas from Newton's second law. For the ideal rope, I project out any radial velocity and snap back to exactly L naught. I record speed and tension for the plots, then repeat over the same time window as the data. And here are the final results, as you can see via the graphs and also the model. The assumptions and overall analysis: the point mass is in 2D on a massless, inextensible 150 feet rope with a rigid anchor with uniform G, no air drag, optional, and tension only reported, no stretch feedback. We integrate the tracker delta T from the measured initial frame. The ideal model fixed length rope captures the arc-shaped geometry and the early time trends. X decreases while Y rises. Speed and tension both peak early as gravity's tangential component drives the motion. The model's period is too long; it hasn't turned around within 4.5 seconds, while the data does. By physics, T is directly proportional to the square root of L, so a too large effective L naught and/or starting before the rope is taut explains the lag. The amplitude or offsets, vertical range and baselines differ slightly, consistent with anchor misplacement and 2D projection of 3D swing. Camera tilt or parallax, and the camera, I believe, is also moving. Damping data shows mild energy loss, non-conservative forces. Air drag reduces speed and shifts the timing, which follows the classic energy principle effect. We plot tension in a stretch estimate. S is approximately equal to T upon K, but do not feed stretch back into the motion. A real rope's compliance near the bottom alters period and amplitude. So sources of discrepancy are error, geometry and calibration, small errors in pixel scale, anchor placement, or camera perspective, 3D swing tracked in 2D, shift the path and timing, model idealizations, no air drag during the run, and an inextensible massless rope, stretch only estimated afterward, change the real periods and amplitudes, and the data initialization, manual clicking noise, CSV sampling jitter, and starting the model before the rope is fully taut can misalign model and data. So our what does it mean questions. At the bottom of the swing, why is the rope tension larger than the jumper's weight? What does this tell us about the motion? From radial, Newton's second law, T is equal to mass brackets v squared upon L naught plus g times r hat. At the bottom, r hat points downwards, so g times r hat is equal to plus or positive g. Hence, T is equal to mass brackets v squared upon L naught plus g is greater than mg. The extra m times mv squared upon L naught term is the centripetal requirement to bend the path into a circle, which is evidence that part of the net force is perpendicular to the motion, curving the trajectory, while the tangential component g times t hat changes the speed. Our what if question is, what if we include linear tangential damping, air resistance in the model? How would the predictions change? Adding f drag, which is equal to negative b tan times v d times t hat, makes the tangential Newton's second law acceleration, which is equal to g times t hat minus b tan times v t upon m. upon L0, the peak speed drops, the jumper reaches the bottom later with a smaller v, and the computed tension curve lowers and broadens. Over time, the model's x and y would show increased phase lag and reduced amplitude versus the ideal case, tending to move the blue curves towards the red data if the real swing loses energy to air and rope friction. So in conclusion, our momentum principal pendulum model captures the arc timing and yields plausible speed and tension, late time gaps versus tracker match unmodeled effect, anchor alignment, drag, rope stretch, or 3D motion. Simple stretch estimates and optional damping explain the trend, and the model is a solid self-consistent baseline. And once again, here are our results from the closed code. Thank you.